Yeah. So yeah, we were just going to start. So in the first problem, I hope everyone has tried it. Um, what comes to your mind? Um, yeah. So if this is the collection of tokens, the problem is saying that we can choose any two tokens, for example, this one, and bring them to their midpoint and stack two of these here. This is one, and these are two. Our objective is to bring all the tokens to a single point. All the tokens here. So n tokens here. So the problem is telling us to prove that we
Can
can,
you please repeat the process once again?
yeah, we choose any two of the tokens. For example, this one and this one,
Yeah, okay. Okay.
and then we bring both of them to their midpoint.
Okay.
Yeah. So and we keep doing this, following a strategy till we get all of the endpoints at a single position. So the problem is telling us that
Oh, like very
this is
close. All the points become very close.
no, not very close at the same point.
Okay, okay. These are points, so they can be overlapping. Okay.
Yeah, yeah. So for example, if there are four tokens, 4 points, we bring these two here. This has two, cardinality two, and the rest of these two here, and this has, yeah, oh, and this has cardinality two, and then we bring both of these.
Oh, so okay. Like when we first do this process and then we get a new point.
Yeah, I mean then these points are deleted.
Yeah, and we get a new point, which is representative of both.
Yes, and then we choose one from here, one from here, and put them here, and then another one
Yeah.
from here, another one from here, and put both of them. So we, all in all, we have 4 points here.
Oh,
um,
okay, okay. So we have to do this also two times.
yeah,
Okay.
I think many new people have joined. So we were just discussing what the statement of problem 1.4 meant. So I will just repeat the process. Yeah, we have a collection of points, and we choose any one of them, any two of them. For example, we choose this point and this point, and we bring both of them. I mean, when I say we bring, we delete the original points, and we say we have 2 points at their midpoint. So these two tokens are deleted, and two tokens are brought here. Our goal is to find all such n being the number of points, so that we can bring all the tokens to a single position. For example, we can do this with 2 points. Given any 2 points, we can bring both of them to a single point, to a single position. The 2 signifies the two tokens here. And given 4 points, We can first bring them to two positions and then bring all the tokens to a single position. So, has everyone understood the problem?
Yes.
Yes.
Okay. So, any ideas
Oh,
on how
we
we can
can
solve?
prove that power of 2 works using induction.
Yeah, that's the easy part. We can prove that a power of 2 works. How does it work? Well,
So if we like take
It's like
uh,
this fourth case, we just take 2 points and we. Oh, but this is in easy case because this is like rectangle.
okay, so like if we take 2 to the power k plus 1 points, if we prove that we can form 2 to the power k piles, in each pile there are 2 tokens, then it is like obvious by induction, right?
yeah.
And we can
So,
like obviously do that by picking up the points in such a way. Like even if there are, let's say, 3 tokens in one pile and 1 token in another pile, we just pick 1 token of that uh, pile in which there are 3, and one other there are 2.
uh, I think we don't need to dwell into that much case with. What we can do is divide them into two parts, two equal parts.
Yeah, yeah, okay, got it.
Yeah, one having, so if the total collection of points has 2 to the k points, if n is 2 to the k, we can divide them into 2 to the k minus 1 and 2 to the k minus 1. Two parts having 2 to the k minus 1 points. By induction, we can reduce this two parts having all the tokens
Oh
at
yes,
one
yes,
point.
yeah,
Yeah, and then we can repeat this process 2 to the k minus 1 times and bring all of them to a single point.
yes, yes. Got it.
Yeah, so clear everyone?
Yes, clear.
Okay, so now for the other direction. Uh, so
I have to
now,
say that in other cases it is not possible.
yeah, in other cases it is not possible. How can we show that?
Uh, we can, I guess, we can also show that, like we show this, like if it is not a power of two, then we can divide, and we will left with some some other tokens, and by induction we know that the power of two will become one stone, and then we do proceed further.
You are saying we divide them into two piles, but
Yeah.
I think, what if the optimal strategy would be to not divide them into two piles? What if we have, suppose, 7 tokens, or suppose 6, and the optimal strategy is to divide them into 4 and 2? I mean,
So
for
like
proving
optimal
it
means
can't
you.
happen, you have to come up, you can't put forward a constructive approach. Are you understanding?
uh, no, like why it is
because
there?
because the optimal strategy may not be to divide the points into two groups. I mean,
Like optimal strategy, you mean the fastest way?
I mean, sorry, the um, the strategy to bring all the points to a single position may not be to divide the whole group whole uh, divide the points into two groups. Um,
Okay. Okay, I got it.
yeah, and it doesn't work for n equals 3. So can you show? Can you give us an example, Rishikesh? Uh, You were saying it works for n equals 3. Maybe not.
An example is not enough, right? It says prove that for every arrangement of n tokens you need to show it.
Yeah, sorry. So, yeah, we'll prove that it works only for powers of 2, but we'll not straight out jump to that. First, we want to understand the problem and understand how this process works. Find out something more
For
about this process.
every time it will work, no? For all arrangements of n equals 3, it will work, no?
No, it won't actually.
Which is the case when it won't work.
Um, when they are the vertices of an equilateral triangle, for example. So, we'll prove that this does not work. But first, let us understand something about this process. So, for the physics lovers among you, this problem um, would have resembled um, a familiar concept. So,
Center of mass.
yeah, exactly. So, if we consider all the points with weight 1, all the tokens, I should say, each time we apply this process, we don't actually change the center of mass. We bring two new points to their center of mass. So we bring these 2 points to their center of mass. And now this has this this point, this blue point has the weight of has the equivalent weight of the red tokens. So this has weight 2. So we don't change the center of mass. The center of mass is an invariant in this process. Is everybody following?
What you mean?
Yes.
What you said last line? We cannot change the center of mass.
Yeah. So in every arrangement, let me go back. So we have this configuration of tokens. We are choosing any two tokens and bringing two tokens to their midpoint here.
Yes.
And because they are two tokens, this token has the weight of its parent tokens, and it is at its parent's center of mass. So we are not changing the center of mass of the whole thing. Yeah. In
Yes.
uh, is everybody following? In a configuration, if we bring two things to their individual center of mass, then this center of mass of the configuration does not change. I mean, we can see this by vectors. Suppose this, we say vectors v1, the points, the tokens have vectors v1, v2, so on till vn. The center of mass has the then the center of mass has
Like
the
a coordinate of midpoint vector v1 plus v2 by 2.
yes,
Oh, the center of
vn,
mass of whole system. Okay.
the whole system. The center of mass of the whole system is this. In an individual process, what we do, we let this part be the same and change these two to v1 plus v2 and v1 plus v2 by 2. So you can see that the center of mass of the system does not change, right? because the sum of all the vectors does not change.
Yes.
So now we are understanding that the center of mass would be this kind of thing, this expression. And this is what we know uh, from the theory of center of mass. But what we know about from the process, so this, then suppose we choose the first token, and suppose token 3. What this changes into is v1 plus v2 plus 2v3 over over 2, comma v1 plus v2 over 2, comma v1 over 4, sorry, over 4 plus v2 plus 2v3 over 4. So, are you seeing something? Focus at the denominators. What can you say about the denominator?
They are powers of 2.
They are always powers of 2. And we can show this how? Because if they are powers of 2 at the n minus 1th step, at the nth step, we are just taking two vectors with linear combinations of vi's over power of 2, 2 to the a, plus some other linear combination of vi over 2 to the b, and we are adding them up and dividing them by 2. Is everybody following here? A linear combination
Yes.
just means um, vi, every vi times some constant. So for example, this expression is a linear combination. We have the coefficient of v1 as 1, v2 as 1, v3 as coefficient 2, and all the other vi's have coefficient 0. I mean, precisely speaking, v1 has coefficient 1 by 4, v2 has coefficient 1 by 4, and v3 has 1 by 2, but you get the point. So at the nth step, what we have is this times some power of 2 plus this times some power of 2, 2 to the b, 2 to the a over 2 to the a plus b plus 1. And we may be able to reduce this fraction, but notice that the denominator, it always stays a power of 2. Yeah?
Yes. Good. Yes.
Anybody else has a doubt? I mean, anybody? Akshay, I'm not able to follow your reasoning. Maybe we'll come at it at a later point.
I wanted to say that obviously for odd number of points it won't work because we are piling them up. For even number of points, if we divide it by the highest power of 2, then if we get a number which is odd, then again it won't work. So it must be powers of 2 only.
Uh, First of all, how can you prove that odd numbers don't work? And second of all, for
If I,
even numbers,
yeah, yeah.
how can you show that the strategy is to reduce them to an odd number? I mean,
Because
this has
when
some fatal flaws.
because if we have odd number of points, say 3, then if I collapse 2 points, so I'll get a point where there will be two tokens and
Okay, okay. Granted, Granted, you have the proof for 3. But what about 101? How will you show that?
Maybe we can induct on the following lines.
Yeah, but I guess that would require casework. Or maybe you have a solution with that. Do try it and let us know.
Okay.
Yeah. So back at this, does anyone have a doubt at this point? Whatever the points are in a configuration, the points always have a denominator which is a power of 2. So if we assume that n is not a power of 2, assume n is not a power of 2, then by what we know, center of mass is sigma vi over n. But because every achievable point has a denominator which is a power of 2, the center of mass has to be a linear combination of the vectors over a power of 2. Because all the points, if all the tokens come to a single position, that position must be the center of mass. uh, because the center of mass stays the same. Yeah, so
Yeah,
does everybody follow
yeah. This
that
this line followed.
these two things must hold true?
Yes.
Anybody else has a doubt, please do tell. Okay.
Uh, at the very start, you write uh, v1 plus v2 by 2 two times. So
Yeah, because v1 also
maintain the sum, right?
goes to that point and v2 also goes to that point. v1
Oh,
also
okay, okay,
goes
yeah,
to v1.
okay, okay. Yeah, now it's clear.
Okay, so but for these two things to hold at the same time, and n is not a power of 2, so n has some odd factor, let's call that d. So in the simplified expression, d has to cancel out. D has to cancel
Yes,
out of
yes,
this expression
right.
because the denominator has to be a power of 2. But this can't happen because all the coefficients here are 1 and all the vectors are independent. So we can't get a linear combination of VIs by dividing D.
Oh,
Is this?
what if the vectors were dependent? Like, how would that affect?
Yeah, for that we are given in the problem that they are placed arbitrarily in the plane for all
Yeah, so vector cannot
positions.
be dependent in that case, right?
Yeah, so in that case vectors cannot be dependent. We uh, we can choose every vi from all points in the plane.
Oh, okay.
So
Like we can imagine this thing. Consider like there are 9 tokens and 3 piles of 3 tokens each. Then you can like cancel out a 3. Okay, like a
yeah,
3 still remains, but I mean like you can still get it, no? Like okay, 6 tokens and 3 piles of 2 tokens each. Then you get the denominator as even, a
so
power of 2.
basically A linear combination with integer coefficients. What I mean to say, positive integer coefficients. So the numerator is a linear combination with positive integer coefficients. But to make this expression, to make this expression get rid of the d in the denominator, we have to sacrifice the integer coefficient part, right? Because the vectors, we can't assume them to be dependent. Oh, okay, Akshay.
Oh, but like in this six token example, there can be like what I said is like three piles of two tokens each. So it is V1 plus V1 plus V2 plus V2 plus V3 plus V3. V1, V2, V3 are still independent, right? And it becomes like 2V1 plus 2V2 plus 2V3. Oh, okay.
Yeah, so in that case, if we have two piles, the
Yes.
numerator may have a common factor with the
Yeah.
denominator, but in the general case, we can't assume that any two are piled or any two have some special property. We can't assume anything. We have to consider all the vectors as independent entities.
Okay, got it. Got it.
Yeah.
Yeah, because there is some loss of generality there.
Yes, precisely. So hence this problem is proved. Yeah, for one direction induction was sufficient, and for the other, noticing the center of mass was had a power of 2 in the denominator, gave the problem away. So which problem would you guys like to try next?
First one.
The first one, okay. Anybody else?
Oh, fifth.
Fifth. Where are the problems? Oh, yeah.
खूपच हो जाए किस. Oh,
So yeah, that hand.
Second one also.
Okay.
yes, let's try second one.
Maybe I can't make a poll.
Oh, the host can make. Okay, obviously.
Yeah. So the second one.
Yeah, I guess there's no objection, so we can do that.
Okay. Second one it is. Yeah. This is a problem I liked. Yeah. So I'll give a minute. Everybody just read the statement and then I'll
All
explain.
these were self-made or was it taken from some source?
No, no, they are taken from sources. I've just not included the sources in case somebody gets
Made.
scared or thinks the problems are easy. I just wanted you to try them by yourself before I reveal the sources.
Okay, okay.
Okay, so now let me tell what the problem means. Construct a tetromino by attaching two by one dominoes. So what they mean by a tetromino is this figure. Okay, this and this. Notice that these two have opposite orientations. What they mean by orientation? Uh, we can have first. Let
L shape
me
is not
draw
a tetromino. Like
an
like
L.
if we
No.
okay.
So these are the four possible tetrominoes. So what they mean by two opposite orientations is that considering this the top left tetromino, we can get to the bottom left tetromino by rotation, a 90-degree rotation, right? And the same for the right two. So these two are of the same orientation and these two are of the same orientation. What the problem tells us that assume a lattice polygon P can be tiled with um, suppose we call these the S tetromino and these the Z tetromino. A lattice polygon can be tiled with only S tetrominoes. Okay. So suppose this is our lattice polygon. This is tiled by only S tetrominoes. What the problem says that no matter how we tile this polygon using S and Z tetrominoes, we can add Z tetrominoes too, but we always have to use an even number of Z tetrominoes. So, is this clear? Is the statement clear?
Yes.
Now, in these type of problems, you know that there are two opposite orientations of a thing, and we have a hint of
Here
hint
only as
of
then
that.
we can use both, no? For means even with Z we can tile it completely.
No, the problem is saying suppose a polygon P can be tiled only with S tetrominoes. Suppose a a tiling with only S tetrominoes is possible. Prove that now if we also use Z tetrominoes, we have to use an even number of Z tetrominoes.
Okay, means we use combination of S and Z, no?
Yeah, in
Not
the second tiling, we use a combination of S and Z.
okay, okay.
So it is given that a hint of parity is given. And in these problems, where there are two opposite orientations, it is often helpful to consider parity.
Yes.
And this seems like a coloring problem. So either we have to color we have to color the plane with color the grid with two colors or with four colors. Yeah, this seems kind of what the intuition tells. After playing around with the problem for a few minutes, we get to know that parity is playing a role here, and the coloring, if it gives a solution, will have possibly most probably two colors, possibly four colors. Yeah. So first, we try to find if there is a tiling possible with two colors. So we just place an S tetromino here. So
Oh,
when
can
I
you give
mean
2 3 minutes for trying a bit?
sure, sure, I'll start the discussion at 7:45. Right?
Thanks.
Okay. We are doing the second problem, Dhruv.
Here lattice polygon means the polygon which has all the vertices lattice points.
All the vertices as lattice points and all the sides as grid lines.
Uh,
That,
that also implies
yeah.
how
So we can't have a polygon like this.
triangle. Triangle we cannot have, right?
We can't have a polygon like this. This is not correct.
Yeah, that is what I was thinking because then we cannot tile it completely.
Yeah. In any tiling problem, you can just assume that it is.
Yeah, yeah. Also, since these two tetrominos are rotations of each other, so we do not distinguish between them.
We don't distinguish between the left two tetrominoes and the right
Yeah,
two tetrominoes.
yeah. And so, like we can say, the leftmost, the top leftmost is the opposite orientation of the beside, which is, and then the opposite, like rotation of
Yeah,
that is,
this one is the
yeah.
opposite orientation of this and the
Yeah.
opposite orientation of this.
Oh, okay.
Oh, I'm not sure if this works. Like in the S, yeah. So like if this is the S terminal which you drew, we color the upper two parts as like the upper two squares as black and the lower two as white. I mean like somewhat of this thing. And uh then the Z terminal should have all the four colors same, something like that, like in the final condition. Oh, Vedant, you are not audible if you're saying something.
Oh, sorry, I was on mute. Uh, I was saying the upper two are black and the lower
Yes,
two.
are white like the other color.
y- Okay.
Yeah. So now if we like in a lattice polygon and color and place the square Z domino, then all the colors of the Z domino should be same. We can enforce something like that.
Uh, your voice is lagging.
Oh,
You are
is it
saying
better?
in all the S tetrominos of the tiling, we
Oh,
color the upper two black and the lower two yellow.
yes.
Okay.
And like then if we replace S trominos with Z trominos,
Yeah.
then we can enforce something like all the four colors of Z trominos should be same.
I think that
Maybe.
does not follow. How, for example, here and suppose this is one and this is one, and so this Z tetromino has three black, one yellow.
Yeah.
Yeah.
But like you cannot also complete properly tile that, no? There will be some squares left. I mean
For
in the
for
polygon.
that you have to come up with a proof or do casework or
Yeah, or like we have to construct that.
yeah. Consider the polygon. Just a
Yeah.
second.
Uh,
No.
if we give an example.
So you want an example of
No, no. You said like we have to prove. So that is what I was saying. Like giving an example, giving a tiling example.
okay. So I think there's some communication lag. Um, what are you exactly trying to say?
No, no. I was saying that he said that
Oh,
there must be
about
some.
Pranav. About
Yeah,
Pranav. Okay, okay,
like
okay.
there must be some squares left. So I was saying that can we give an example that will uh, indicate that all the squares can be tiled.
Okay. So the problem with his approach is that uh, all tetrominos, we can't ensure that all Z tetrominos have four uh, colors, have all the four squares of the same color. They can be 3 and 1, 4 and 4, 2 and 2. There is no guarantee if we do that coloring. So that does not work. But what you notice is that when you place an S tetromino and a Z tetromino like this, what we want is to have a Z tetromino cover an odd number of each color and S tetromino cover an even number of each color. This should be clear by this time, because if this is the case, then when we tile with only S tetrominos, we have an even number of black squares, even blacks, to maintain that with the S and Z
Oh,
tetramino tiling.
how you are coloring?
I've not actually colored uh, till now. I'm just saying what the coloring should look like. What properties must the coloring have?
Okay.
That we must color the board in such a way that every Z tetramino covers an odd number of black and an odd number of yellow, and every S tetramino covers an even number of black and even number of yellow. If we
What's
do
black and
this,
yellow?
sorry,
Means how are we coloring black and yellow?
uh, yeah, that's what I'm saying. We haven't yet, colored the board yet, but
Okay.
we will.
Hmm.
What I'm saying is we make some observations about how we want the board to be colored, which will help us to color the board. Yeah. So if we get a coloring like this, then we can ensure the polygon P has an even number of blacks because we can tile it with only S tetraminos. And in the tiling with S and Z tetramino, every S tetramino will cover an even number of blacks, and every Z tetramino will cover an odd number. So if there are odd Z tetraminos, the total is even plus an odd number of Z tetraminos into odd numbers. I mean, plus every Z tetramino covers an odd number. So an odd number of odds is still an odd, right? Even plus odd
Yes.
equals odd, and we get a contradiction because we knew that P, the lattice polygon, had an even number of blacks. Is this clear?
Can you please repeat your reasoning
Yes.
again?
Yeah, I'm saying if every S tetramino covers an even and every Z tetramino covers an odd number of blacks, then in P there must be an even number of blacks. And
Okay.
in the coloring, in the tiling with both S and Z tetraminos, S tetraminos, all S tetraminos will cover an even number of blacks. And if there
Okay,
are an
understood.
odd number
Running
of,
away getting bored. Okay, okay.
so understood?
Yeah, yeah, understood.
Yeah. So following this heuristic, what we can say, what can we say about this positioning? That this is an the red one is an S tetramino. It must cover an even number of black and even number of yellow cells, and the blue one is a Z tetramino, which must cover an odd number of black and an odd number of yellow cells. Notice,
Oh, maybe we color like the end ones as black and the middle two as yellow.
not exactly. What we can say is that these three squares, they are common to both, right? So
Yes.
whatever is in these three squares is common to both.
Right.
So if the endpoints are also of the same color, suppose this is yellow and this is yellow, then are you getting something? Both of them will have the same parity of black and yellow,
Yes.
right? So for them to have different parities, what we can say is that these two endpoints must be of different colors, right?
Yeah, because we want them to be of different varieties.
So we can say that if this is black, then this must be yellow. So every pair of cells, two to the right and two up have different colors, because we can repeat the same analogy here. We have this cell and we have this cell, uh, this tetromino and this tetromino. So by the same thing, we get thus this square and this square have different colors, right?
Yes.
So
Right.
every two cells separated by two rows and two columns, separated by one row and one column, must have different colors.
Oh yeah. Yeah. Right.
Yeah, in the coloring we want.
Yeah. So this means that, like, how do I write? Like, if we there is the black color, and then if we go down one, two, three, four, five steps, if we go down, then that will also have black color.
Yeah, so you mean to say, sorry.
Yeah, yeah. This is right,
Yeah, yeah,
because
this one.
we can just place tetrominos like that.
Yeah, so what we can say is now that these all will have black colors. Sorry. And
Yes.
by this, we can say this, this will have yellow colors, right?
Yes.
And
Yes.
now we
Uh,
can't make
so
any other
al-
progress.
also this is not an infinite board.
We have to consider it, no, because the lattice polygon can be arbitrarily large.
So like we
So
are
we
considering
have to,
infinite. It is infinite.
yeah, yeah, we have
Okay.
to consider plane, the
So
whole plane as a
then I
board.
guess then I guess there is no issue, because this will just continue like this.
Yeah, yeah, this will just continue.
Yeah.
So now we are stuck. Now we can't make any further deductions. So we just randomly try to color. Suppose we color this yellow. Then we can say this is black, this is black, this is black. Same for this, and this must be yellow, this must be yellow, this must be yellow. Right?
Yeah.
Now again, there seems we can't get anything out. So we again try something.
Oh, the above two are black and that red one because of our play. Ah,
No,
both
we
of
can't
them
get
are.
that. We can't get that, right? Both can be yellow too.
Ah, okay. Mhm.
So
Yes.
suppose both are black, right? Now what do we get? Now things start to open up. So then we have um, these, and these two must be yellow. These two must be yellow, and these two must be yellow. Same for these two. And then we can say these two are black, right? Yeah.
Yeah, we can say.
Okay. And then again, it seems we don't have enough. So we take this to be black. Now we can make more progress, because this is an S tetromino. The lower square must be yellow,
Uh,
and because this,
How did that S tetromino came?
for any S tetromino, we have to color such that any S tetromino covers an even number of yellow
Mm.
and black squares,
Yeah,
right?
but like it is not
That is the
given that
procedure we have
there is
defined.
the S tetromino, right?
uh, uh, Someone's spoke in between, can you repeat?
Like, but
Like
this is, but it,
Yeah,
we have defined the procedure.
excuse me, yeah, Pranav was speaking first, let him complete, then we'll
Yeah,
come
yeah.
to
okay,
you.
okay.
So like it is not necessary that there is a S tetromino there. Like you were coloring and then you randomly placed it. No.
Yeah, what what we want is we place an S tetromino anywhere in the grid. It covers an even number of colors, even number of
Yeah, yeah, that
yellow
is
and
what
black
I was
colors.
going
Ah,
to say.
okay. Okay, fine,
Okay.
got it.
Yeah, Akshay. So, are you able to follow? Yeah. Huh. Can you understand that any two squares separated to this is of one color, then this square must be of the different color, right? Is this clear? Oh, so I guess I would have to repeat. So what we want is any S tetromino has, we just put an S tetromino here and a Z tetromino here. The middle three squares are common to both of them, right?
Okay.
Okay. So if the end squares have the same color, then these two tetrominoes have the same parity of colors, no? Because they have the same set of colors.
Okay, yeah, understood.
But what we want here,
Odd and even.
they have different set of colors. So any two squares separated by one row and one column have different
Master.
colors.
Yeah, yeah, understood.
And we are just following the same logic over and over again to color the board. We are just
Okay.
following this heuristic, right? So now um, we can get this is a black square from this, and this must be a black square. Now this is a is an S tetromino, so the remaining square must be a yellow square, and similarly for this is a Z tetromino, so the remaining square must also be a yellow square. Now note that this one is a Z tetromino, so the remaining has to be a yellow square, and we repeat this process, right? So we repeat this.
Okay.
We keep repeating this. For black, mm, sorry, I made a mistake. You can color these yellow. You can color this yellow. This is yellow. Now this must be black. So it's this. And what about This is also black. This is black. This is black. This is black. This is oh, this is yellow. This is black. So, are you able to see a pattern here?
Yeah, the for the like for the Z, yes, for the Z tetromino, I guess the starting point and the ending point are right, same.
Okay.
That is why they have the same color.
So, this coloring, what we get is a bunch of windmills, right? A
What?
windmill like shapes.
Oh, okay. Oh, right. You are right.
This one here.
सही है.
No. And you can verify that every coloring. Oh, I made a mistake here. This one must be black,
Yeah.
and this one is not black. Sorry for that. So, yeah, so continuing this pattern, we get windmill like shapes, right? And you can verify in any position. If we put an S tetromino, it will cover an even number of squares. For example, we put it here, even, here, even, here, even, here. We bring it down, it doesn't change. We rotate it, the same. So if
This is wonderful.
someone, yeah, sorry,
This coloring is nice. I think we can do using this.
yeah, Raghav, we are discussing the second problem. So what I wanted to stress on is that if somebody randomly just gave you this problem and showed you this coloring, you would have no idea how to get here. Yeah, you can't think this coloring could be thought in a reasonable amount of time. But actually, what this coloring actually needed
No, like
was,
what you did is that you build up, you start in the center and then just follow the steps.
yeah, I took some motivation from my intuition
Yeah.
that what we want in the problem is that every S tetromino covers an even number of squares and every Z tetromino covers an odd number of colors, I should say. And the fact that they overlapped, they were so similar in pattern, they overlapped. So I just made a few clever deductions and that helped me to unravel this whole problem. I just found this problem very nice and this motivation. So I decided to put it.
Yeah,
Oh,
yeah.
this is
This
IMO
approach was
shortlist.
also
Uh,
very slick.
this is IMO shortlist 2014 C4, I think. Yeah.
Oh, okay.
Someone in the chat asked. Yeah. Everybody satisfied with the proof? Any doubts or we can move on?
No, no doubts.
Okay. So which problem next?
This category of fall problems, does it fall in graph coloring?
Not graph coloring. Coloring. This is just coloring problems. Board colorings. There is no graph here.
Okay.
Yes. Yeah. Just coloring problems. Tiling problems. Coloring problems. Yeah. Any preferences? Yeah, the first, the third, and the fifth.
Fifth.
Okay, you say fifth. Anybody else?
Yeah, let's do.
Okay, so yeah. So what this problem says is that we have five integers at the vertices of a pentagon: 6, 5, -10, 0, 100. What we can do is choose any two adjacent vertices, suppose these two, add or subtract, however you wish to say it, a common integer, the same integers. Suppose we subtract 5, we subtract 5, so this becomes 95, this becomes -5, and the opposite to the opposite integer we add 10, 5 plus 5, so this becomes 15. Yeah, simple enough. So the problem says that the sum of the five integers, it should be clear that the sum does not change when we do the process. The sum of the five integers is 2011. uh, the problem says us to prove that for any choice of initial integers there is exactly one vertex at which the game can be won. Now what this means is that if the game can be if the game can be won, we have to show that it can be won at exactly one at only one vertex. Yeah, no two vertices. Not on two vertices can the game be won. And exactly one means the game has to be won. We have to show that we can win the game. That we can, uh,
Yeah, this is one player game.
yeah, one play game.
And what you said about 2011.
That the sum of all integers, sum of the five integers is 2011. So at the
Or like
end,
we have to take in that manner, so
taken,
that the sum is 2011.
yeah, we are given some five integers in order so that their sum is 2011, and
Okay.
at the end we have to make them such that four of them are 0, and this the fifth one is 2011. Now we
Okay.
have to prove that we can make four of them 0 and one 2000, the first part. And second part, if we can make if we can reach this configuration, this configuration is not possible.
That is, the first part is given, or we have to prove it?
We have to prove.
Where is it written?
Yeah, the last
There is.
line: for any choice of integers there is exactly one. Exactly one means not 0, not more than 1. Exactly one, so the game has to be one, the first part.
No, no,
And
this part where they are saying that there are four zeros and 2011. Where does it say that we have to prove that this orientation is possible?
Yeah, we have to prove that. It's only given that the sum of all five is 2011. We
yeah,
have to prove that that the game can be won at this position where there are four zeros and 12011.
That I understood that we have to prove at that position.
yeah, what exactly haven't you understood? uh, Let me explain that.
They are stating that the game is won at a certain vertex if after some number of turns
Yeah,
that vertex
okay.
has the number 2011. So that's
And the other four vertices have the number 0
yeah. So we have to prove that this orientation occurs for only one point. That we
for
have to
only
prove.
one vertex.
Okay.
Yeah, and this orientation occurs, this also.
We have to first prove that this orientation has to occur.
Yeah, or
No,
you
no,
have to
because
prove
that part,
that
second
if
part we cannot prove anyhow if you don't prove first.
that may or may not be true. Oh, so we are running short on time, and I would really like to finish one problem. So I guess you would have to sacrifice your solving time. Let me get on with the solution. Is everybody fine with this?
Yeah, give
Okay.
motivation
Yeah.
also.
Okay. So this problem shouts out that we have to use an invariant, right? Because
Yeah, yeah, exactly.
yeah, first we prove the part that if it can be one, it has to be one at a single point. Yeah, it would have been beneficial if you were to try these problems beforehand, Akshay. But no problem. Yeah. So we have to find an invariant such that for that invariant, this configuration and this configuration, these two configurations give different outputs, right? So in other words, what it is saying that it is not vertex dependent. So every vertex has a different share, if you can say so, in the invariant. I'm talking loosely here, no rigorous stuff. So every invariant has a different part. Yeah. I was going to come to weight. So what we can do is we say this vertex has number A, this has B, this has C, D, and E. So here A is 2011, B is 0, C is 0, D 0, E 0. So there would be an invariant T, suppose, which be weight of A times A plus weight of B times B plus weight of E times E, and this would be so weight of I, well, weight of something is not equal to weight of some other thing. Yeah. And because oh and because we have to bound the invariant somehow, because it doesn't give that much properties, right? It doesn't characterize the configurations. So probably we have to consider this mod some number, right? Of
Yes.
course,
Yeah.
this doesn't come when you look at the problem. It comes when you try different configurations, when you get to know a problem better. But this probably would come to your mind at some point that we have to choose different weights for different vertices and to characterize them into different groups, different classes. We probably have to take mod some number, right? So when the invariant finally is revealed, it is a very unique invariant if you have not seen those before. But for now, we have to slog through some algebra. So what it is saying that suppose we choose A and B and transfer their contents to D, right? So what we are doing is in the invariant we are subtracting weight A minus weight B and adding weight D to weight D, and this is congruent to T mod n. Right? Everybody with me?
Yeah.
Okay. So what we can just say is that 2 weight of D, weight of A plus weight of B on n. We write similar expressions. Copy paste. Okay, so probably that's enough. Weight of B, weight of C, A. Yeah. Oh. To C, D, E, B, C, D, E, A. Yeah. So if you start substituting for weight of A, then weight of B, what's the motivation? We know it is very common for an invariant to be uh, some sort of weighted sum of elements. So in this case, the elements are the numbers at the vertices, and we are choosing the weights so that the weights have to be different, because yeah, the weights have to be different because if the weights are same, um, we can the two vertices may be the two vertices contain the same properties, right? In a loose manner of speaking. So the weights have to be different, and when we change, when we move, they don't change. The invariant doesn't change. So now, if you go through and substitute each of weight A, weight B, weight C, you will find that n does not work for any value other than 5. Okay, you get probably something like 5 WA minus WB equals 0. I vaguely remember this expression. So we know that these two are not the same, or some, it is probably symmetrical, but I don't really remember. So this is not true. So 5 congruent to 0 mod n. So n has to be 5. And now, if you randomly choose weight A equals 1 and weight B equals 2, you find that weight C now has to be equal to 3, weight D has to be equal to 4, weight E has to be equal to 5 or 0, as you prefer it. And this would have worked out no matter what value of uh, weight A and weight B we would have chosen, as it turns out. So Doing some guesswork and following some heuristic often helps you to get to the core of a problem. So now we have the invariant WA plus 2WB plus 3WC, I mean times A times B times C. Oh, A plus 2B plus 3C plus 4D plus 5E mod 5. This becomes the invariant. And you can check that this value does not change whenever we do the process, right?
Yeah, it seems it won't change.
So now it is left to prove the part that we can do this. We can reach one vertex. All the every other vertex has 0 and one vertex has 2011. For that, note that 2011 is not divisible by 5. So at any point A, B, C, D, E are not all divisible by 5. So in the original configuration, there exists um yeah, so if suppose this are the original set of numbers we are given, we just compute yeah, sorry for this. We know that this, suppose the invariant is congruent to 3 mod 5. Okay, suppose we are given some numbers a naught, b naught, c naught. These were the numbers we were given, and we calculated this. We had weight 1 here, 2 here, 3 here, 4 here, and 5 here, and t turned out to be 3 mod 5 because 2011 is congruent to 1 mod 5. If only one vertex is 2011 and the others are 0, so it must be here. 2011 must be reached here, right?
Yes.
Because the invariant is 3 exactly at c naught, at the place c naught. So we have the uniqueness criterion. We have shown that it can reach, if it can be reached at only one point. Now that it can be reached, for that, notice that given any two vertices adjust at distance 2 or 3 from each other, we can do this set of moves. 0, 2, and where we have moved these two, then 0, where we have moved these two, then this, where we have moved these two, right? So given uh, two numbers separated by a position, we can bring them to one position. Okay, and if they are not separated by a position, we can obviously bring them to one position. So what we do is, we bring each one of them here, add to this, so one of them becomes 0 and the other um, is an integer, and do the same thing here. So one of them becomes 0 and the other uh, adds to this value, or D would become 0 and C would add, but it doesn't really make a difference. So yes, so suppose D is 0 and C is here. So now what we can do is A and C. By this process, A and C, one of A and C will become 0 and the other one may stay an integer and deposit to B. Now we have reduced the problem where we can, where only two positions are non-zero and the other are 0. At this point, suppose 2011 was to be reached at this square. Yeah, we can calculate beforehand where 2011 has to reach depending on the invariant we took. So suppose it has to reach here, then we convert this to here. So one of these becomes 0. Suppose this becomes 0 and this is some positive integer, and no, so for example this is C, we subtract B. Okay, so this becomes 2B, this becomes 0, this becomes C minus B, and then we add B plus C. So this becomes 3B plus C, this becomes 0, this becomes 2B minus C, sorry, B minus C. So we can bring the integers with 3 are 0, one is at the desired endpoint and the other one is some is at a different point. So this is A, this is B, suppose. So now what do we know? Oh, I've exceeded. So let me just finish here and leave the rest to you. So what we can do is we can transfer. So actually this must be the one where we have, where the weight is 5. Okay, where the weight is 5, we bring one of the uh, integers to the position with weight 5 and one of them is elsewhere, and then uh, because uh, oh, I'm really confusing myself, sorry for this, but the end lies in proving that we can shift 5 of these to another position. So 5 can be shifted around and this lets us finish the problem. So I hope you will complete it from here, and this is where the session ends, I guess. Thank you. Any doubts?
Should I stop recording?
Yeah, sure.
Thanks a lot for this session. This question were like previous question